Hello, and welcome to the Chapter 4.4 online lecture on nonhomogeneous linear equations with constant coefficients. So the key word here is nonhomogeneous. In the previous section, we learned how to solve homogeneous linear equations with constant coefficients, and now we're moving on to nonhomogeneous ones. So recall that given a linear differential equation L of y equals g of x, and a general solution y sub h, to the associated homogeneous equation L of y equals 0, obtained by just deleting the right-hand side and making it homogeneous, and given a particular solution to the original differential equation, then the general solution to the original differential equation is y sub h plus y sub p. We just put together our solution to the homogeneous complement with any particular solution to the original differential equation. And in 4.3, we learned how to solve homogeneous linear differential equations with constant coefficients. So we now know how to get this. And the topic of this section is getting that y sub p. And if we can get that y sub p, then combining it with 4.3, we have our general solution to non-homogeneous linear differential equations with constant coefficients. So this is just an example from a previous lecture. For this differential equation that was a fundamental solution set, here is a non-homogeneous differential equation. And we found that a particular solution to that was negative 1/6 x. And this was the general solution to the homogeneous complement. So all we did was add together that yh and yp. And the method that we used to get this y sub p, you may recall that we just kind of guessed, in a sense, with an unknown coefficient, and then solved for it by plugging in. And that is the method of undetermined coefficients, which is the primary way that we'll be dealing with solving these in this section. So for example, find a particular solution to this differential equation. Well, looking at this, if we take the derivative of some scalar multiple of e to the x, it's still a scalar multiple of e to the x. Same with the double derivative. You take the derivative of e to the x itself. So we guess maybe y sub p is k times e to the x, or some constant k. We plug in, and we have that. And the derivative of e to the x is itself. So this becomes simply this. And now adding together, we have this. And writing that another way, that's 2k e to the x is 1 times e to the x. And if this is true for all x, then that means that 2k equals 1. And thus, k is 1/2. So a particular solution is 1/2 e to the x. And we can combine this with our knowledge of finding general solutions. So at this point, we have found that a particular solution is 1/2 e to the x. We know that the general solution is yh plus yp. So we have our yp. Now we need to find our yh. And yh is the solution to the homogeneous complement obtained by simply deleting the right-hand side. And we learn how to define that. We look at the auxiliary equation. R is 2 and 3. So therefore, yh is c1 e to the 2x plus c2 e to the 3x. And now our y, which is yh plus yp, is c1 e to the 2x plus c2 e to the 3x plus 1/2 e to the x. Is our general solution to this non-homogeneous linear differential equation. So that's the method. We find yh, we find yp, and we add them together. And we find yp via this method of undetermined coefficients. So what we're going to be learning how to do is how to correctly, quote, guess what form to plug in order to get a particular solution. So in this case, the right-hand side was e to the x, so we guessed k times e to the x, because the derivative of e to the x is itself. How about this one? So here the left-hand side is the same thing, only difference is now the right-hand side is e to the 2x. Well, the derivative of e to the 2x is 2e to the 2x. Derivative of that is 4e to the 2x. So if we add those together, it looks like maybe we will get e to the 2x with an appropriate scalar coefficient. So let's guess y sub p is k times e to the 2x. So let's pre-compute the derivatives. And now plugging in, we have this, and we have pre-computed those derivatives. Good. And now adding these together, we have 4 minus 10 plus 6 is 0. That is a contradiction. That means that this guess didn't work. There is no solution of the form k times e to the 2x. What went wrong? Why was this different from this? The only thing that we changed was e to the x on the right-hand side to e to the 2x. So what went wrong? Well, recall that YH, that was C1 e to the 2x plus C2 e to the 3x. And that means that any scalar multiple of e to the 2x is automatically 0 after we plug into the left-hand side. After all, as a solution to the homogeneous complement, what that means is that if you plug it in, it's equal to 0, by definition. So we could have known this, that we would get a 0 on the left-hand side there without doing anything, if we had realized that. So the moral is that k to the 2x was already a solution to the homogeneous complement, so can't work. And what we do is, if what we would guess is already a solution to the homogeneous complement, multiply our guess by x. So instead of guessing k e to the 2x, we'll guess kx e to the 2x. And avoiding this situation that we just encountered is why we always want to find the solution to the homogeneous complement y sub h first. So always find y sub h first in order to tell in advance if this would happen, and we need to modify our guess from the start. So here that is our YH as we have found, and we would guess YP is k times the e to the 2x, but that is already a solution to the homogeneous complement. So instead we guess YP is kx e to the 2x. Let's pre-compute our derivatives since we need to plug this in. So by the product rule, YP prime is that f prime g plus fg prime. This is a product of two functions. And now the second derivative, okay, there's the derivative of that part, and over here, we apply the product rule again, and we have that. So that's what we got. We plug in, okay, and we have pre-computed these guys. Now we'll gather together all like terms, the like terms meaning all e to the 2x pieces, and all x e to the 2x pieces separately. So first, all plain e to the 2x pieces, that's 4k e to the 2x minus 5k e to the 2x is simply negative k e to the 2x. And now all x e to the 2x pieces, we have a 4k there, minus 5 times 2k is minus 10k, plus 6k, 4 minus 10 plus 6 is 0, x e to the 2x. And that must be equal to our right-hand side of e to the 2x. So you can see what happens. The x e to the 2x part goes away. And what we wind up with is simply negative k e to the 2x is equal to e to the 2x, and thus negative k is equal to 1, equating coefficients. You might be wondering, wait, can't I just divide both sides by e to the 2x? Yes, you can in this case. But I'm introducing it this way of equating coefficients because in a bit we'll be needing to guess linear combinations of other things. and that will require actual equating of coefficients, so we're just getting used to it now. So we have that k is -1, so yp is negative x e to the 2x. And now we could combine that with our y sub h, and we would find a general solution to this. Now, what about this? So remember, first, we always want to find y sub h. You always want to find y sub h first because of this moral, where we don't want to guess something that's actually a solution to the homogeneous complement. So we have y double prime minus y prime minus 6y is 0, is the homogeneous complement. That's r squared minus r minus 6 is the auxiliary equation. That's r minus 3, r plus 2. And we have that yh is c1 e to the negative 2x plus c2 e to the 3x. Okay, so sine x is definitely not among those two. It's not among these, so we need no correction to our guess, i.e. no multiplication by x. The kind of multiplication by x that we had to do in the previous example. So what is our y sub p? Well, let's think through this. If we plug in some scalar multiple of sine x, okay, we'll have a sine x there. The derivative of that is cosine. Double derivative of sine is derivative of cosine is a negative sign. So we'll have something like a sine, cosine, sine. So if we plug in k sine x, it looks like that actually won't work because we'll wind up with a cosine, and what we want is the right-hand side, and thus left-hand side, to be exclusively sines. So what we want to do is, because the derivative of sine x is cosine x, we want to guess a linear combination of sine and cosine. So because the derivative of sine is cosine, that accommodates that y prime part. And then for the y double prime, the double derivative is negative sine, and these are, we want to think of it as basically the same thing up to scalar multiplication, which is all we care about since we're taking scalar multiples anyway. However, these two, the point being, are fundamentally different. They are linearly independent. And that's another way of saying that those two are really the same thing. They are scalar multiples, linearly dependent, while these two are fundamentally different. And what we want to do is guess an arbitrary linear combination of the derivatives of the right-hand side, since we're taking derivatives. So why is it that in the previous example, we only had to guess a scalar multiple of the right-hand side by itself? Well, that's because the derivative of e to the 2x is 2e to the 2x. And then also the second derivative, therefore, the same thing applied. So when we plugged in, it was all scalar multiples of the same thing. A single one-dimensional space on the left-hand side was introduced, aligning with that one-dimensional space on the right. Okay, but here that situation is different. So that's our guess. So we have yp as k1 sine x plus k2 cosine x, for all the reasons just discussed. And let's pre-compute the derivatives. So that's the derivative of the function and the second derivative. And now we'll plug in. So we have this. So this is our yp double prime minus yp prime, and then minus 6 times yp, that's our yp, equals sine x. And now we gather like terms, by which we mean gather together all the sines and all the cosines. So what is the coefficient of sine after we gather them together? Well, we have a negative k1 sine, minus k2 sine, minus 6k1 sine. That's a negative 7k1 plus k2 times sine. And then what is the coefficient of cosine? Well, we have a negative k2 cosine, negative k1 cosine, negative 6k2 cosine. In total, that's negative k1 minus 7k2 cosine x is equal to sine x. And now what we do is we equate coefficients, because this equality needs to hold true for all x. And that means that the coefficient of sine here must be the coefficient of sine there, and this coefficient of cosine there must be the coefficient of cosine here. What is cosine? Over there, where is it? Well, there's an invisible plus 0 cosine. So then we equate these coefficients, and we'll have a system of two equations and two unknowns. So we got this system of equations from plugging in our guess and equating coefficients. Now let's solve that. We can do this in a few ways. Let's do it by elimination. Let's add 7 times the first equation to the second. And then we have negative 50k1 minus 7k2 plus 7k2 goes away, is the point, is equal to 7. So k1 is negative 7 over 50. And therefore negative 7 over 50, plugging into the equation, minus 7k2 is 0. And thus k2 is 1 over 50. And recall this was solving for the coefficients k1 and k2, and yp is k1 sine x plus k2 cosine x. So therefore we have our particular solution of negative 7 over 50 sine x plus 1 over 50 cosine x. Okay, so we already knew that yh was c1 e to the negative 2x plus c2 e to the 3x, and we got that a particular solution is negative 7 over 50 sine x plus 1 over 50 cosine x. So our general solution, which is yh plus yp, is just combining these two. There's our yh, and then plus yp is minus 7 over 50 sine x plus 1 over 50 cosine x. Yes, the problem only said to find the particular solution, but just illustrating the general solution. So how in general can we figure out what form to plug in and guess? Well, our reasoning here was that because the derivative of sine is cosine, and then the derivative of cosine is sine again, then a linear combination of sine and cosine should suffice as a guess for a solution. And this generalizes. Here is the theorem on how to find what to guess. And by the way, this is not in the textbook. But now that we know our language of linear independence, we can formulate this well. Given a linear differential equation with constant coefficients, then if all elements of the set of derivatives of the right-hand side, so g, g prime, g double prime, etc., can be generated as linear combinations of finitely many functions, f1 to fn, none of which is a solution to the homogeneous complement, then guess an arbitrary linear combination of them. And if one of them is a solution to the homogeneous complement, then just multiply all elements of it by x. That's what we did over here. K e to the 2x was already a solution to the homogeneous complement, so we just multiplied our guess by x and instead guessed kx e to the 2x. So let's illustrate this theorem. And we can first illustrate it here, or what we already did, just to show the application. So we know that yh is c1 e to the negative 2x plus c2 e to the 3x. That guy is our g of x. And the set g prime, g double prime, etc., that is sine, cosine, negative sine, etc. And these are all of the form k1 sine x plus k2 cosine x. So we guess that, which is exactly what we did. This is what we mean by them all being a linear combination of finitely many functions. These are all of the form k1 sine x plus k2 cosine x. That's a linear combination of sine and cosine, generates all of them. Let's do this one. So we always want to find the yh first, because then we might realize we need to multiply by x. And here yh is that same thing. G of x is that right-hand side, x squared. And the set of all derivatives of g of x that is x squared, 2x, derivative of that is 2, derivative of that is 0, derivative of that is 0, etc. And all of these are of the form k1x squared plus k2x plus k3 times 1, full stop. For x squared, the coefficients are 1, 0, 0. For 2x, the coefficients are 0, 2, 0. For 2, the coefficients are 0, 0, 2. And then for everything else, it's 0, 0, 0. So all of these are a linear combination of these three functions. So we would guess a yp of this form. Let's do another. What would we guess for this? Okay, so here yh is that same thing. And e to the x sine x is not one of those, so we don't need to worry about multiplying by x or anything. And what is the set G, G prime, G double prime, G triple prime, etc.? Well, so G is e to the x sine x. The derivative of that by the product rule is that. The derivative of that, again by the product rule, is 2e to the x cosine. The derivative of that by the product rule is that, etc. And you can see that no matter how many times we take the derivative, the product rule will just keep an e to the x times either a sine or a cosine. So all of these are of the form k1 e to the x sine x plus k2 e to the x cosine x. So we would guess k1 e to the x sine x plus k2 e to the x cosine x. And we would plug that in and equate coefficients the exact same way that we did in the previous example. And we will get a system of equations with k1 and k2, which we can then solve, and we'll have our particular solution. What about here? What would we guess? So looking at the right-hand side, you might think, oh, that's the same thing. We guessed the same thing. But remember, you always need to be careful of if what you would guess is a solution to the homogeneous complement. The homogeneous complement is obtained by just deleting that right-hand side. And this is 1 plus or minus I by the quadratic formula, which we know how to plug in and get. And that means that YH is C1 e to the x sine x plus C2 e to the x cosine x. As we found on the previous slide, we would guess k1 e to the x sine x plus k2 e to the x cosine x, but that is already a solution to the homogeneous complement. So what do? We multiply our guess by x. Since that being a solution to the homogeneous complement means that if we plug it in, we automatically get 0 on the right-hand side, not e to the x sine x. So we would guess instead k1x e to the x sine x plus k2x e to the x cosine x is our form of the guess. And we plug that in, we'll get a system of equations with k1 and k2 after we equate coefficients, just like we did, and solve. And remember that you can always check your work by asking Wolfram alpha, which you won't have on the final exam. But according to Wolfram alpha, I put in this same equation, and it solved it for us. So yes, there's the solution to the homogeneous complement, and it looks like our particular solution is -1/2 e to the x times cosine x, which was exactly the form of our guess. So it looks like k1 would have been 0. There's no e to the x sine x, and then k2 would have been -1/2. Let's do an example where the right-hand side is constant. We might even be able to do this by inspection. So remember, first always find YH. YH is C1 e to the x sine x plus C2 e to the x cosine x, as we found. And 6 is definitely not a solution. It's not in the homogeneous complement. What is the set G, G prime, G double prime, etc.? That is 6, 0, 0, 0. Are all of these linear combinations of some single function? What the fuck? Oh my gosh, it's the dog. Yeah, you stay out of here, dog. Sorry, you scared me, dog. I didn't mean to scare you. So are all of these linear combinations of some single function? Yes, they are all linear combinations. K1. Technically K1 times 1, if you want to think of the actual function of which they're linear combinations. For 6, that's K1 equals 6. For 0, that's K1 equals 0, etc. So we just guess YP equals K. That's it. YP is going to be a constant. And this is super easy if we plug in. Well, the derivative of a constant is 0. So when we plug in, we just have 2K equals 6, and thus K is 3. So YP is 3. So go ahead and think, what would you guess as a particular solution to this differential equation? Encourage you to pause the video. So remember, first you always want to find the solution to the homogeneous complement. The homogeneous complement is y double prime minus 2y prime is 0. That has auxiliary equation r squared minus 2r is 0, factor out the r, and r is 0 or 2. So yh is c1 e to the 0x plus c2 e to the 2x. That is the same as c1 plus c2 e to the 2x. Okay, and here, what is the set g, g prime, g double prime, etc.? Well, g is x, derivative of x is 1, derivative of that is 0, etc. So all of these, are they all linear combinations of some finite set of functions? Yes, they are all of the form k1x plus k2 times 1, technically. So do we therefore guess yp is k1x plus k2? Well, is one of these a solution to the homogeneous complement? Yes, right there. We can think of this as c1 times 1. So the answer to this is no, that is not what we guess, because that 1 in what we would guess is a solution to the homogeneous complement. So what we do, we modify our guess by multiplying it by x. So instead we guess yp is k1x squared plus k2x. And you can see that now neither of those is a solution to the homogeneous complement, so we're good. Now, given that we now know that we want to guess k1x squared plus k2x, go ahead and try your hand at solving this differential equation. Pause the video. All right, so it's always a good idea to pre-compute your derivatives so you can easily plug in. So the derivative of yp is that, the derivative of that is that, and now we can plug in. So we plug in our guess yp, and we have 2k1 minus 2 times 2k1 x plus k2 is equal to x. That's our y double prime minus 2y prime. Now we gather like terms. So let's gather together all the x's, of which there's only one, negative 4k1x. And then the constant terms, that's 2k1 minus 2k2. And that is equal to x. And now we need to equate coefficients. That's our x term, that's our constant term. What's the constant term over here? Well, we can imagine this as a plus 0 times 1. And here we have a plus that times 1. And the coefficient of x is 1. So our equating coefficients looks like this. The x coefficients are the same and the constant coefficients are the same, i.e. the constant terms are the same. So we have the system, negative 4k1 is 1, and 2k1 minus 2k2 is 0. From this first one, we don't need to do any elimination here, it's just k1 is negative 1/4. And from the second one, k1 is k2. And therefore, k1 is k2, and they're both negative 1/4. So our particular solution is negative 1/4 x squared plus 1/4 x. And if you plug that in, you can see that it satisfies it. And our general solution is just yh plus yp. So therefore y, which is yh plus yp, is that. So here we had to multiply our guess by x because our original guess would have already had an element as a solution. Now, I don't think there's any situation like this on the homework, but I should point out that if after you possibly need to multiply your guess by x, as we did in this example, then part of it is still a solution to the homogeneous complement, then you need to multiply by x again. In other words, no part of your guess can be a solution to the homogeneous complement. That would only occur in the case of a double root, though. Let's conclude with this homework problem. So looking at this, we have a fourth order differential equation. We always want to find yh first. So for yh, we want to solve this homogeneous complement. That's r to the fourth plus 2r squared plus 1 is 0. Looking at this, here's a slick way of doing it. We can think of this as r squared squared plus 2r squared plus 1 equals 0. And that factors as r squared plus 1, all squared equals 0. In other words, we're just regarding this r squared as a single thing, and then it becomes factoring an ordinary quadratic. And thus, we have r squared plus 1 equals 0 as a double root, and thus r is equal to plus or minus I, square root of negative 1, as a double root. So what does that mean yh is? Well, we'll have c1 sine x plus c2 cosine x. Remember that this is 0 plus or minus 1 times I. So this is using our formula for the case of a conjugate pair of roots. And e to the 0, the e to the alpha x that would be here, that's just 1. So anyway, it's that, but it's a double root, so then plus c3x sine x plus c4x cosine x. So that's our y sub h. And what is our y sub p guess? Well, think g, g prime, g double prime, etc. That will be x minus 1 squared, 2 times x minus 1, 2, 0, etc. And looking at this, and this is one of the main points of this example, in addition to that factoring trick for getting the solution to the homogeneous complement expediently. That's our set of derivatives. And are all of these linear combinations of some finite set of functions? Well, they're all a sum of a constant, a scalar multiple of x, and a scalar multiple of x squared. So they're all of the form k1 x squared plus k2x plus k3. And none of these is a solution to the homogeneous complement, so that's our guess. So we'll guess k1 x squared plus k2x plus k3. And we'll plug that in and equate coefficients and solve. And when we equate coefficients, that means we need to gather together the x squared terms, the x terms, and the 1. But in its initial form over here, there is no x squared term, x term, and 1. The whole thing is squared. So what we need to do is write this as x squared minus 2x plus 1. And then we can equate coefficients. So just be mindful that if the right-hand side is some polynomial like that, FOIL it out, and that way you can then equate coefficients easily. And yes, unfortunately here you'll get a system of 3 equations and 3 unknowns, but usually with polynomial guesses, it is slick to solve. You'll immediately get one of them, for example, like we did in the previous example with a polynomial guess. So let's not finish that. We know how to plug in and equate coefficients and solve the system of equations, and we know what form to guess, and therefore we know how to use this method of undetermined coefficients to solve non-homogeneous linear differential equations with constant coefficients. That concludes section 4.4. Have a great one.